All right. So I'm going to go through this first portion of the note sheet, just so that if I am either absent or you wanted to kind of come back and you missed something, then you have this part as well. So this will be part one. The other one is, of course, posted as part two. So when we talk about properties of acids and bases, a lot of your questions were based off of this. What is a base? What is an acid? For acids, they actually taste sour. And you're like, why are you saying how it tastes? We can't eat our chemicals in the lab. And you are right. But in real life, a lot of things that we eat, it kind of shows you there in that last bullet point is they are acidic, right? A lot of vinegar-based things, a lot of citrus fruits, citric acid. So those are just things that we have in terms of acids there. Of course, they can burn your skin, especially if they're super strong. We'll talk about that here in a second. Of course, the pH is less than 7, right? 7 being neutral. We talked about that in our simulation. And this is a really important one right here. It releases H plus ions. That's really what creates and what makes acids because they have these hydrogen ions that are there. And when they're in solutions, they actually split up, and all of these hydrogen ions are just floating around. So if I had a little beaker of stuff, there'd just be a bunch of hydrogens floating around there. It'd make this an acidic substance there. They do react with metals, and that's what you kind of saw in your stations activity, where only acids would bubble, fizz, change temperature, change color, so on with the metals. But they don't appear color, so there's no color change. You can say that they remain clear with phenolphthalein, which is an indicator. So this is an indicator, kind of like the universal indicator, and we label that as PHTH for phenolphthalein. That's how we abbreviate that. And again, common in food products. You can kind of see there lemon, soda, tomato, coffee, and all that fun stuff. So the closer we get to 7 on the scale, the more neutral we end up being. But for simplicity's sake, we're saying that pretty much everything that isn't 7, that's less than 7, can be considered acidic. Now, of course, most are slightly acidic to, more strong, or stronger, I guess you would say. And of course, if you had to say what the stronger acids are, they are, of course, closer to 0 or closer to 1. And then, of course, the weaker acids are a little bit closer to that neutral area there. Over here, we have bases. We put bases as blue. That's what they appear in as, or in a universal indicator. These taste bitter. All right, think of if you ever had soap in your mouth, and that taste, that is definitely bitter. It feels slippery. So if you got any base on your fingers in the lab area, you would notice that it has some slippery substance. It feels slick. Greater than 0 or than 7, of course, is the pH value. And again, very important here. Releases OH ions. The OH ions are, again, what make a base, or what we say is alkaline. And of course, if the acids react, the bases do not react with the metals, and they appear pink with phenolphthalein. Again, this is an indicator that you're going to use in lab, and we abbreviate it PHTH. And common in cleaning products. So a lot of our cleaning products are basic, kind of like soap, ammonia, bleach, a lot of those different types of things. So when we're going through, we're identifying our bases. It's pretty much everything that's got a pH level above 7, of course, which is neutral. And just like kind of like a mirror image of the acids, the weaker bases are closer to 7, right? And the strong bases are closer to that 14 threshold, right? And that's the limit to our pH scale. And you might be thinking, well, what is going on with, what is going on with water, right? Why is water neutral, right? And you might be thinking, oh, it's it's water, right? Everything deals with water, everything uses water, which is true. But I want you to just kind of think about, what's happening here. If you have acids which contain an H plus ion and all of your bases contain OH, well, what if you put those two things together and have them maybe in equal amounts, right? Then you don't have something too acidic, you don't have something too basic, you actually end up with water, right? H2O, right? An H with an OH, hydrogen ion and a hydroxide ion there. So that kind of puts into perspective that, water actually, and we call it amphoteric, it can be an acid or it can be a base. And we talk about that a little bit more in part 2 with the development of hydronium ions and such. So that's just a little bit of nice little background there and connection. But we're going to get into some calculations. That's why I have the calculator pulled up. So when we're talking about this, you'll see that there's a lot of brackets here. These are kind of like little mini formulas to help you out in your worksheet. And I go through a whole worksheet with this stuff as well in another video. But you see that this nice little square kind of helps you connect everything, right? You see the direction that the arrows kind of touch each other show you what information you can get based on what you have, which is really nice. And I like putting the brackets around the ions just because what those brackets represent, whenever I have brackets like this around there, this is a hydrogen ion. Again, that's what makes an acid an acid. And with the brackets around it, that just means concentration of hydrogen ions. All right, and we're going to be using, kick it back to our solutions unit, the idea of molarity, right? The molarity, the concentration of those ions that are floating around in any solution that we have. And then we also have, of course, our bases, which are comprised of these OH, or hydroxide ions. And again, that just represents the concentration of hydroxide ions. And we measure that in molarity as well. All right, so that's what these bracketed ions there show. And it also kind of shows you another thing where this term P, right, if I wanted to just kind of isolate P here, that P means negative log in math. So when you talk about pH, you're really talking about negative log of the hydrogen concentration. And same with POH, right, where it's the negative log of the OH concentration of ions there. And then, of course, if we have one way to figure out the POH and the pH, then we should be able to go backwards. Now, these are log base 10s, which mean that to go backwards, all I have to do is take those pH values and put them to 10 to the power of those. So we'll do that here a couple of times so that you can see. All right, so if we go down and kind of fill out this chart a little bit, I'll do a couple up top and then I'll do a couple toward the bottom just so that you can see. What we want to do is we want to, again, just familiarize ourselves with long notation versus scientific, right? Scientific notation always starts with a decimal after one whole number, times 10 to the something, right? So in order to get this number right here, we just have to figure out, okay, well, how many times do I have to move this decimal forward or backward to get this, right? And so I see that I moved it back once to get 0.1, which means that this is negative since I moved it backwards, and 1. And of course, concentration is measured in molarity. So these two numbers right here, they are exactly the same value. They're just written differently, right? Scientific notation versus long or standard form. The pH, again, is the negative log of the H concentration, the concentration of hydrogen ions, you can say. Right, so if I know the concentration value, then I should be able to just type into my calculator, like I will here, negative log of 1 times 10 to the negative 1, or you can put 0.1, it does not matter, and then I plug it in, and then I get a pH of 1. All right, and the cool part about this is you do the pOH values the same way, negative log, because that's P, of the OH ions. But now look, we don't have the concentration of the OH here, so we can't just plug a value in here like we did before. But the beauty of the pH scale is that if we look up here at some of our nifty formulas, the pH and the pOH both have to add up to 14 because you see, that's the extent of which our pH scale reaches. So if I know one, I always know the other, which is a nice way to connect those. So all this is 14 minus 1, which ends up being 13. And from there, what I can do is I can use this value here to go backwards and figure out what the specific concentration of those OH ions are. And how I do that is by reversing this log. And how I reverse a log is by taking 10 and I put it to the negative, in this case, since I'm looking for OH ions, the pOH. So 10 to the negative 13 here is going to give me the concentration of the OH, which is going to be 10 to the negative 13. And that gives me 1 times 10 to the negative 13 molarity there. All right. Now, I do ask you whether or not this is acidic, basic, or neutral. And again, you have these two values now. You have a pH value, you have a pOH. You're like, which one do I use? Well, you can only use pH to figure this out. Right? We read things and base acidity and basicity and neutrality off of the pH value. So the pOH value is just a counterpart. We don't really use that. So here we have to use pH. All right, so we look, pH is 1. Well, that is quite acidic, so this would be an acid. So we use, again, the pH value to figure that part out. So let's do another one. And notice I'm given something different. In this case, I give you the scientific notation. Now, we're going to be primarily using scientific notation, but again, it's a nice review to kind of be able to know what long notation would be. So over here, I see that this is a negative 3, which means I'm going to move backward with my decimal, and I'm going to do it 3 times. So it would be 1, 2, 3, and that didn't work out. 1, 2, 3. All right, so the decimal ends here, and every hump that I create is a 0, right? So I'm going to end up with a longer notation of 0.001 molar. And that's those two numbers, again, are the same thing. The way that and not to confuse you with that, but the way that I did that was I just moved the decimal back however many times it told me to. Notice you'll always end up with 1 fewer 0 than what your exponent is. So my exponent is 3, and I have 2 zeros. And it always works out that way because the decimal going back in front of that number that it's behind actually doesn't create a 0 there. Coming over here, to find the pH, we do the negative log of that value. You can use either value, so I'll show you doing the long notation now. It's the same thing, 0.001. That gives me 3 as my pH. Now let's do negative log of 1 times 10 to the negative 3, just to show you that it's exactly the same value. All right, so I have my pH. Well, because I have my pH, I can figure out my pOH, which is going to be 11. And then I can use the nice reverse log, as I like to call it, to use the pOH to find the concentration of those OH or hydroxide ions. So that's going to be 10 to the negative 11th, which is going to be, I'll prove it to you here, 10 to the negative 11, 1 times 10 to the negative 11. So 1 times 10 to the negative 11 molarity there. Is this acidic or basic? Well, I look at the pH value. I see that the pH value is 3, which is less than 7, which means this is certainly an acid. Right? So let's go to this bottom one here. I'm going to just jump around and do a couple. I'm not going to do all of these to save you time as well. But let's go to this one right here. So I see that I have a pOH value that I'm given, which means that I can find two things right away. I can find the pH value, because the pH value would just be 14 minus that, which is 7 as well. And then I can use the pH and the pOH values to figure out the individual concentrations of the hydrogen and hydroxide ions there. So doing that, let's do the pOH first, since we're given that. The pOH is 10, or the hydroxide ion concentration, right? The OH minus, right? That's going to be negative pOH. So 10 to the negative 7, which is going to give us a concentration of 1 times 10 to the negative 7th molarity, right? Molar solution. And then for the hydrogen ions, I do the exact same thing, but I just use the pH value. So I do 10 to the negative pH, right? Because now I'm dealing with the hydrogen ions. And that's going to be 10 to the negative 7 as well. And we notice that those are the same concentration. Well, that should make sense, because when I have a pH of 7, that means that I have something that is, neutral, right? And neutral means that I have the same amount of acid and base in this same space. And look at that. I certainly do, right? The concentrations of both are equal to each other. So this kind of checks out. And then it's obnoxious to write this in long notation. But remember, negative means going backwards, and I'm going to have one fewer 0 in front of that 1, or in front of that front number, than I have as my exponent. So I'm going to end up with 6 zeros in front. So this is going to be, and the 0 before this decimal doesn't count, right? So it's 1, 2, 3, 4, 5, 6, and 1. And that's why we use scientific notation, because that's an obnoxious number to have to write in long form. Let's do one that is, let's do one of each of these. So let's do these two, and then you can kind of fill in the others by yourselves. So you'll see that I did part 2 before part 1, because, that's how we roll. But here we're going to figure out, by using the H concentration, what the pH should be. We're going to also do the long notation. So same rules apply, even though we're not using nice numbers like 1 anymore. So because the exponent is 3, I'm going to have 2 zeros in front of that front 2 there, and it's going to be going backwards because it's negative, so I should end up with 1, 2, and then my 2, 3, 5. And I'm going to write the 2, 3, and 5 because it tells me all 3 of those numbers, so I want to make sure I include them. And Finding the pH value, again, is just doing the negative log of the H concentration, 2.35 times 10 to the negative third. And we get a pH value of 2.63, right? Now I can figure out the pOH, 14 minus 2.63. 2 decimal places is fine for all these, 11.37. And to figure out the pOH, 10 to the negative 11.37, because I'm using the pOH to find the concentration of OH, or hydroxide ions, which is about 4.27 times 10 to the negative 12th molar. Right? What is this? Well, it's always based off of the pH. The pH is less than 7, which means this is an acid. All right, and one more for good measure. Let's do this one down here where we start with a pH value. And again, I start with a pH value. I can find a bunch of things. Let's find what's the easiest first, which would probably be the pOH, because it's just 14 minus that. So 14 minus 8.32 is 5.68, right? So now that I have my pH, let me write those here too. pH, just so that you don't get lost from above. Now that I have both of those, I can figure anything else out that I need. Let's look at the concentration of hydrogen ions here. All I have to do is reverse the log, so that's 10 to the negative pH there, 8.32, and we get 4.79 times 10 to the negative 9th molar for molarity. And then I get 10 to the negative 5.68, which is 2.09 times 10 to the negative 6 molar for my hydroxide ion content. And let's do this, because this is going to be a bummer. But because it's a -9, I'm doing it in long notation. Negative means move the decimal back this way, and I'm doing it 9 times, which is going to result in 8 zeros before that 4. Remember, 1 fewer 0, so the 0 in front of this decimal does not count. It's a placeholder. 1, 2, 3, 4, 5, 6, 7, 8, and then I have my 4, 7, and 9. Yep, scientific notation looks much better because it's a lot less to look at. And then, of course, is this acidic or basic? Here's the pH value. It is above 7, not much, so very weak acid, or very weak base, but it's a base nonetheless. There's our base. All right, so again, just kind of using these formulas here to help you out there. So there's even more examples. I went through the entirety of 1103. So this is all based on assignment 1103 up here. So I went through all that. There's a whole video key for that entire worksheet to help you out and have more examples. One last thing I want to kind of show you, and how this is really cool, is notice how we determined that, and we'll look at this one, for instance, that this is an acid. And we see that because of the pH value, right? And that's pretty straightforward, less than 7. But I want you to just pay attention to the actual concentrations of the H and the OH, right? OH is base, H plus is acid, right? Hydrogen versus hydroxide. But this -12, that is a really, really, really small number. Look at how small -9 was. To the -9th, that's a very, very low number. So it only makes sense that we don't have a lot of OH ions in this solution because it's an acid. And we have much more hydrogen in here, right? So again, you can kind of check your work and be like, well, does my answer make sense? Well, yeah, because, 0.0 0.00235 is a much, much larger number. It's crazy to say, is a much, much larger number than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 427, right? That's the discrepancy between how much hydroxide's in here compared to how much hydrogen's in there. So again, just another way to kind of show the difference between checking yourself too. So hopefully this helps. Work through this, and then let me know if you have any questions.